So here we have some numeric columns and some categorical columns. And this is the target we need to predict, the sale price of the house. We're going to start by looking to see if the data set is complete. We're going to do that using df.info. And we can see that we're missing a couple rows here and here. We're just going to replace them with zeros so we don't lose any data. But you should usually give more attention to this, see why they're missing. Let me start. Yeah. Then now we want to, when we look here, we have some couple numerical columns and some categorical columns. For the numerical columns, we might want to standardize them so they're on the same level, so we can compare the different columns with each other. And for the categorical ones, we want to make sure we separate them so the model understands them. We're going to use that. We're going to do that by replacing them with the dummy variables. So for standardization, we're going to use this one. So this small function. So the standard scalar from the scalar library. And as an example, this is the z-score you remember from your stats class. And when we're first starting, before any transformation to the data, before getting the z-scores, we're going to have something that's wild, has a huge mean, a huge standard deviation, but we want them to be on the same scale. So after we apply the transformation, all of them are going to have the zero mean and unit standard deviation. And for the dummies, if you guys look at this example data we have here, so it's just 1, 2, 2, 1, 0, 1 through 2, it just repeats. And if we use pd.gets dummies, just changes them to 3 columns, so the number of classes they are, the number of categories, and if the category is in that observation, it's just going to say 1, and if it's not there, it's going to say 0. So that's all it does, because if you look here, it's just strings, and the model won't understand strings. So we're going to also think about doing a future engineering here. We can see that there's a year build column and a year remodeled column. And some of them, it's the same, but most of them, it's different. And maybe we can use this to get a relative age of the house when it's sold. And that's essentially what we're doing here. We're just subtracting year remodeled from the year built, or so the opposite. And then we're going to drop the these 2 rows, the columns, because we use them here. And then we want to standardize all the numerical columns. And we're going to do that here. We're going to loop over all the numerical columns except for sale price. And then we're going to apply the standardize function. The competition where we got the data from wants to compare the logarithm of the sale price and the predicted price. So we're also going to take the logarithm here. Moving on, we want to split the data into train, test, and validation. I don't know any out-of-the-box implementations of this, so I got this from Stack Exchange. You usually just have train, test, split, but we also want validation here. And this function does exactly that. We're going to use 70% of the data for training, and the rest is evenly split between validation and test. There we go. Oops. Then we're going to move on to models. To compare the models, we want to have our metrics. our scores function is going to take the actual sale price or the logarithm of the sale price and the prediction. First, we're going to look at the root mean squared error between the actual and the prediction. And then we're going to look at the R squared between the actual and the prediction. For linear regression, we're just going to import it from scikit-learn, and then we're just going to call linear regression. Then we're going to call fit on X train and Y train, which is the training data and the associated label. Then we're going to run predict on X validation. It's going to give us the predictions. And we're going to compare that with the actual value and the ones we have. And we're going to end up with this score, these two scores. We're going to do the same for the decision tree, the exact same format, just fit and predict. And then we're going to put these into the score function to get this output. And then we're going to do the exact same thing for random forest and also for support vector regression. So far, is it clear? Okay. Then we're going to move on to hyperparameter tuning. So what this is all these models, if you go do this, come up with some set parameters, and some of them we can play with, like the kernel, the degree, the C, the regularization factor. So we might want to check all the different values they might have and maybe get a better model that way. So we're going to define a dictionary which has the parameter name as the key and the values it can take as the value. So I'm basically going to test the kernel hyperparameter, make it the radial-based function, make it poly, make it linear. And I'm going to test a different set of values for C and also the degree. So this is going to find all the possible combinations of these and run all those models and compare them. And then it will bring me the one that works the best or has the smallest scoring function. So the grid search object will help us do that. We're going to give it a model. We're going to give it a parameter grid. We're going to give it a scoring function in a string. We're going to give, so this is for cross-validation. So we know it's not just a data set, it's actually significant. And we're going to give n jobs equals -1 to use all our CPU cores to run this in parallel because it's going to be many models. So then we're just going to call fit. This is going to run for a while. For me, it took 40 seconds. And then we're going to use the predict method to get predictions. Then we're going to compare it with the actual. And then we're going to do it with the testing. And then finally, we're going to also print what's the best estimator. What's the best estimator out of all these parameters. And this is what we're going to end up with. And in this case, we didn't actually improve the model that much, even though we tested all of it. But usually you would get like a slight decrease in the maybe RMSE score and a slight increase in the R square. And that's basically it. Does anyone have any questions?
Awesome. Thanks, Umar, for that presentation. If anyone wants to reference what Umar just went through, I believe he sent the link into the chat of this presentation. So basically, from now on, I'll run you guys through the more in-depth version of the problem definition, and then you can break off into your teams and start coding. Let me share my screen. All right, let me know if you guys can see that. Perfect. So basically the fashionableness data set, as I alluded to in the earlier presentation, is made up of 70,000 images like this. The way that these images are represented is they're 20 by 28 images. However, in the Excel file, I'll pull that up. So the way the Excel file, or the way you'll get the data, is each row of this Excel file is one image. So the first column is the label, which corresponds to one of these 10 numbers. And then the remaining rows are the pixels, pixel 1 to 784, I think. And so basically, in order to be able to view images like this, you'll have to manipulate the array or the data into a 20 by 28 grid. So that's kind of your first task. I write a lot more about it here, which I will send to you guys. So you will take this Excel sheet, which has the labels associated with the images. In order to train your model, you'll divide this into an 80-20 or 75-25 split, whatever you guys think works best for the problem, and train and validate your model on this. And then you will use that model to use or predict the classes of this sheet. And this is essentially the same, obviously different images, except for there's no label column. So you will use your model to output a 10,000 integer array with the predictions for this. After that, you will output that prediction array with the class numbers into, let's see if this opens, an Excel sheet or CSV like this, which is just one column with all of your predictions, which obviously won't be 7 in all of your cases. And then this CSV will get pushed to each of your team's GitHub, and then I'll use this predictions to evaluate the accuracy of your model. In order to solve this, I would advise using Jupyter Notebook because it allows for staged code execution. If you don't have that set up on your computer right now, that's a good first task to do, is just Google how to get that running in your Python environment. If you're really stuck, I can send you a PDF with in-depth instructions, but it's good to practice self-directed learning. In terms of libraries that I would suggest using, a lot of them are similar to what Umar used in the tutorial there. But again, you can find a lot more information on these on the internet. I spoke a little bit to the submission requirements. So please submit your files with exactly that naming convention. It'll cause me a lot of headaches if everything's different. Most of your teams should already have a GitHub, because Ian kind of talked to all of the one member from each team and got that set up. In the event that your team does not have a GitHub, please create it and share it with my GitHub username listed there. And then finally, I just have kind of a rough outline of the flow you should follow. Any questions about any of that?
Questions.
All right, awesome. Well, in that case, you guys can all break off into your teams and start coding away. The next event we have is the DCL workshop at 12:30. So if you could all join that, that'd be awesome. Feel free to message me with any questions or any of the DODs, Sydney, Willem, or Tabasum. Awesome. Thanks, guys.